A visitor from outside our solar system just swept past the sun, and it might be older than the sun itself. Not slightly older, possibly billions of years older. Scientists pointed the James Webb Space Telescope at it, and what came back changed. How researchers think about objects arriving from other star systems. This is one of the strangest confirmed space stories of the past year. Start with the basics. Our solar system has one sun, 8 planets, a collection of moons, and countless smaller bodies. Asteroids, comets, all bound by the suns, gravity looping around it on repeating paths. Everything that orbits the sun belongs here, in the sense that gravity keeps it locked into that path indefinitely. Every so often, though, something shows up that doesn't belong at all. Something that formed outside our solar system entirely, passing through our neighborhood exactly once before leaving forever. These are called interstellar objects. And in all of recorded human history, we've only confirmed 3. The first appeared in 2017, small, oddly elongated tumbling through space in a way that kept people talking about it for years. The second arrived in 2019, behaving much more like a familiar comet, complete with a visible tail and clear cometary activity. Both came and went, quickly fading from view, before telescopes could fully study. It's worth slowing down on those first 2, because understanding them makes it much clearer why the third turned out to be such a big deal. The first confirmed interstellar object was unlike anything on record, moving on a path that made clear it was bound to the sun with a strange elongated shape that made headlines worldwide. What made it so puzzling was how quiet it was. Almost no visible activity, no obvious gas or dust streaming off it, the way a normal comet would, which made it extremely hard to study in detail. By the time telescopes fully grasped what they were looking at, it was already too far away and too faint to learn much more. It left more questions than answers, and parts of its behavior are still debated today, simply because there wasn't enough time or data to settle them before it disappeared. The second interstellar object, arriving about 2 years later in 2019, behaved very differently. A clear, glowing coma, a visible tail acting much more like the comets astronomers already knew from our own solar system. Because it was more active and easier to observe, scientists gathered a much richer data set on its chemistry and structure. Even so, by the time telescopes were tracking it closely, it too was already departing, limiting how much could be learned before it slipped back into deep space. Both encounters left scientists hungry for a third opportunity, a bigger, brighter, more active interstellar object, with enough advance warning for the worlds. Best instruments, including tools that didn't even exist back in 2017 to get a proper look. That's exactly what happened next. On July 1st, 2025, telescopes at a survey station in Rio Hurtado, Chile, spotted something moving fast across the sky. The station is part of a network called the Asteroid Terrestrial Impact Last Alert System telescopes, built specifically to scan the sky every clear night for anything that could pose a risk to Earth. That night, the system flagged a faint, fast-moving point of light. Astronomers checked its path, and within days had their answer. This object was moving far too fast to be captured by the sun's gravity. It was going to loop back around. It was going to pass through and continue out into deep space, never to return. This was the third confirmed interstellar object in recorded history. It was eventually named 3II Atlas, the 3, marking it as the third of its kind. Atlas, honoring the telescope network that first spotted it. Right away, something about it stood out. Its path around the sun was more extreme, more sharply bent than either of the 2 objects that came before it. The shape of an object's path reveals how strongly or weakly it's attached to the sun's gravity. A gentle looping curve belongs to our solar system. A path that comes in fast bends only slightly and shoots straight back out is just passing through 3. I-Atlas had the most extreme, most sharply hyperbolic path ever measured for an interstellar object, moving at well over 2,000 to 2,000 kmh when first discovered, and it only kept accelerating as it fell toward the sun. Here's where things get genuinely startling. Based on how fast this object is moving relative to the average motion of stars in our part of the galaxy, scientists estimated roughly how long it's been drifting through space since it was first flung out of whatever star system it originally formed in. That estimate placed its age somewhere between 3 billion and 11 billion years. Our own sun and solar system, for comparison, are about 4 or 5 billion years old, meaning it's entirely plausible. This comet is older than the sun itself. It may have formed around a star that existed and died long before ours, ever ignited, drifting alone through the galaxy for that entire stretch untouched until it happened to cross paths with our solar system. a frozen fragment of another solar system, possibly older than our own, drifting close enough for our telescopes to actually study it. Unlike the first interstellar visitor, which looked largely inactive and rocky, Atlas turned out to be a genuinely active comet. As it approached the sun-frozen surface, material began turning directly into gas, streaming away, and forming a glowing coma along with a faint tail. That activity mattered enormously to scientists, because an active object releases its internal chemistry into space where telescopes can actually detect and analyze it. A quiet, inactive rock keeps its secrets. An active outgassing comet gives them up. It's also worth appreciating the coordinated effort behind even finding this object. The survey system that caught it scans huge swaths of the night sky every clear night, comparing each new image against the one before, looking for anything that moved. Most of what it catches are ordinary asteroids, safely orbiting within our own solar system. The system exists mainly to flag potentially dangerous asteroids early enough to calculate any risk to Earth. Catching a genuine interstellar object at all is a rare bonus, a needle in an almost unimaginably large haystack of nightly sky images. And catching this one early enough to give astronomers worldwide months of advance warning before its closest solar approach gave scientists something they never really had with the first two visitors: real lead time to plan detailed observations rather than scrambling at the last minute. Once its hyperbolic interstellar path was confirmed, observatories and space telescopes around the world began lining up to take their turn, studying it. The James Webb Space Telescope, often just called JWST, or Webb, is the most powerful space telescope humanity has built. It doesn't see light the way our eyes do. It's tuned to infrared light, longer wavelengths that let it pick up heat signatures and chemical fingerprints, invisible to ordinary telescopes, making it ideal for reading the exact chemical makeup of faint, distant objects like comets. Webb wasn't originally designed with fast-moving, small solar system objects in mind, and tracking something moving as quickly as 3I Atlas pushed its tracking systems in ways they weren't really built for. Despite that, engineers and astronomers locked Webb onto the comet in August 2025, capturing its first detailed spectrum, essentially a chemical fingerprint made of light. After the comet swung around the sun and began heading back out, Webb observed it again in mid-December 2025, with a different instrument tuned to mid-infrared wavelengths, capturing the most detailed chemical readout ever taken of an interstellar. What came back surprised a lot of scientists. The comet's chemistry didn't match typical comets that formed in our own solar system. It showed an unusually high ratio of carbon dioxide to water vapor, breaking from the pattern astronomers have observed for decades in homegrown comets, hinting that whatever environment this object originally formed in was chemically different from our own solar neighborhood. Then came a bigger discovery. Buried in the mid-infrared data, scientists identified a clear signature of methane gas streaming from the comet, the first time methane has ever been directly detected coming from an interstellar object. Alongside the methane and carbon dioxide, Webb also picked up a clear water vapor signal, plus something genuinely unexpected, a specific atomic signature belonging to nickel. Finding a metal like nickel in a comet's escaping gas is unusual, and it tells scientists something about the raw ingredients mixed into this object when it first formed, likely billions of years ago, around a completely different star. Methane matters here because it's an extremely simple, lightweight, fragile molecule, the kind that breaks down when exposed to raw cosmic radiation over long stretches of time. Exactly the bombardment an object drifting alone through interstellar space for billions of years would face with nothing to shield it. Because of that fragility, scientists didn't necessarily expect to find much methane left on the outer surface of an object. This ancient finding a strong, clear signal was a genuine surprise, and it pushed researchers to think carefully about where it was actually coming from. The leading explanation, the comet's outer layers had lost much of their original methane over billions of years of exposure to deep space radiation, and what Webb picked up was methane escaping from deeper unprocessed material, underneath material shielded from that radiation for billions of years, only now being exposed as the outer layers boiled away in the heat of our sun. In other words, Webb wasn't just reading the surface of this ancient visitor, it was reading material that had been locked away since before our own solar system existed. Webb wasn't the only instrument on this comet. NASA's Hubble Space Telescope observed 3I Atlas both shortly after discovery and again after its solar pass. Hubble's early observations gave scientists a rough first estimate of the size of the comet's solid nucleus buried beneath all the glowing gas and dust. Later observations, once activity had settled after the sun pass, allowed a cleaner measurement separating the faint glow of the solid core from the much brighter surrounding coma. Estimates shifted somewhat as more data came in, but the most refined measurements put the nucleus at roughly 2 5 kilometers across, noticeably larger than either of the two interstellar objects discovered before it. That larger size is part of why 3I Atlas became so much brighter and easier to study than its predecessors. More surface area means more material heating up and releasing gas near the sun, which means a brighter coma and a stronger chemical signal for instruments like Webb to lock onto measuring a comet's solid nucleus precisely is genuinely tricky, since the tiny core is almost always drowned out by the much brighter surrounding gas and dust. Astronomers combined brightness measurements at different wavelengths with modeling of how reflective different surface materials tend to be to isolate that faint core signal, which is part of why nucleus size estimates for 3I Atlas narrowed over time as more observations came in. Other instruments joined the effort, too. SphereX, a space telescope built to survey the entire sky in infrared, took its own look in December 2025. Picking up signs of increasing activity after the solar pass, along with dust made of tougher, more heat-resistant material, mixed into the coma, plus additional gas signatures. Ground-based radio telescopes using ALMA observations chipped in as well, detecting other molecules escaping the comet, including methanol and hydrogen. Cyanide adding still more detail to the picture of what this ancient visitor is actually made of. Because 3I Atlas moved on such an extreme path and turned out to be surprisingly large and surprisingly old, some corners of the internet ran with speculation that it might not be a natural object at all. That's a fairly normal human reaction to something this unusual, and scientists took the curiosity seriously enough to actually check. Researchers pointed radio telescope arrays specifically built to search for technosignatures. Any artificial radio signal suggesting an object was built, rather than formed naturally directly at 3I Atlas during its passage through our solar system, listening across a wide range of frequencies. The result was clear. No artificial signals were detected. Every piece of data collected from Webb's, chemical fingerprint to Hubble's, imaging to the radio searches, points to exactly what an ancient natural comet should look like. Its behavior matches known cometary physics. Its chemistry, while unusual, fits within the range expected from an icy body formed around a different star. Its coma gas, emissions, and dust all line up with a natural interstellar comet rather than anything constructed. Worth saying, plainly the real verified science here is already remarkable enough without embellishment. A confirmed visitor from another solar system, possibly billions of years old, carrying chemical fingerprints frozen since before our own sun existed, studied directly by our most advanced space telescopes, that's already one of the more remarkable natural discoveries of the decade.